Yeah, just talked about the rectifier and how that works. So, all right, so on to more general terms here about these things. So, note that all voltage meters need current flow to register. Note that all voltage meters need current flow to register. So here, voltage meters actually read current. Read current flow calibrated to show volts, based on Ohm's law. Based on Ohm's law, which is current flow is proportional to voltage, which I don't think I need to write. And that's not uncommon at all in aircraft at all, for something to read one thing calibrated to show something else. Like earlier I talked about how in fuel injected engines, there's a gauge that tells the pilot what the fuel flow is, but it's really just a pressure gauge that has been painted to show flow, basically saying, well, if the pressure's this, the flow must be this. And so as long as everything is correct, then that's what it's going to show the pilot. So that's why I was saying that if the pressure starts going up, the pilot's going to go, oh, the fuel flow goes up. Well, it didn't, because there was actually a restriction. So, yeah.
Wasn't number 3 iron thing?
Yeah, like I said, don't even start with that. It just, sometimes I stop, I put something in. Yeah, it'll make you crazy, and it'll make me crazy if I try and figure it out at this point. So I always preface it with, don't worry about that. Yeah, it was, but now I've got this. It says also 3.
Okay.
So.
Stop.
Okay. Sometimes it gets bad enough, I'll just use circles and squares and stars, and then nobody complains.
Not the test.
Not on the test. Okay, so, what else? Well, I've got an exhaust gas temperature gauge in my aircraft, which is a voltmeter that is showing me temperature, which is really common. So you can see this in a lot of different things. Let's see, most meters have about 100 degrees, that's as far as a circle goes, not temperature, 100 degrees of usable range. Again, that's a circle, not temperature. It's not Fahrenheit. Of usable range due to principles of magnetism. Which is the magnetic force. The magnetic force acting on a substance is inversely proportional to the distance. The magnetic force acting on a substance is inversely, meaning kind of the opposite, inversely proportional to distance. Which is to say, and I'll write that, move this up. There we go. See, that problem solved. Now we don't have the 3 anymore. Let me see. Which is to say, the further the distance, the less the force. The further the distance, the less the force. So meters can only read a certain range. Before the magnetic force is out of range. Range before the magnetic range, or force is out of range. All that to say, now you know why Simpson meters are square and not round.
What?
Well, it's only 100 degrees. That's why they doesn't make it in a circle. You don't have a circle, and the thing goes. Okay, shifting gears a little bit here. And I think this is something that I kind of threw in like the last year or so, and I'm like, well, we gotta kind of cover this a little bit because you're going to see these a lot, and there's not a lot of questions that are going to pertain to this, but you're going to see them, so you kind of have to know what it is. And it's a Wheatstone bridge circuit. And I don't have a picture of one, so I will have to draw one for you. All right, so they always look like this for whatever reason. Because heaven forbid we would make it a square, make it a diamond. All right, Wheatstone bridge, and we can add to that. There we go. And we can put G for a galvanometer right there, and we'll put a little switch there. Oh, we could have put a switch here too for on off. So Wheatstone bridge circuit. And I'll give you some numbers. So we'll put this R1, R2, R. By the way, I used to draw all the other ones, the D'Arsenval and the Wheatstone, or we do Wheatstone, and all the other stuff. So people say, "What did you just draw? That looks terrible." All right, so this is a widely used type of circuit. You see it in all kinds of things. So I'll just give you an example of what it's doing. So a widely used.
Hey Kevin, can you give me like 30 seconds to catch up?
Yeah.
Sorry.
I'll just write quietly to myself.
I love it. I want to listen to you, but I'm trying to draw this.
Could you imagine if I used PowerPoint? This is already done, and I just hit click, 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 click.
Oh. There's a reason I failed out of school. Teachers did that.
I actually had somebody who's no longer employed with the district who insisted that I stop writing on the board and go to PowerPoint because it was the wave of the future. Well, it's not my future. You right? You ready?
What's that? What's the one say? RP?
RP.
What's that?
Resistance P. Oops, this one's actually RX. So make that an X. If I stick with my drawing, that way it'll work out here. Okay, so a widely used type of circuit. These are all kinds of things, but I'm going to say type of circuit used for measuring resistance. And that's kind of how this one's gonna work. Let's see, B. Resistors 1, 2, and 3 are precision variable resistors. And the reason why they're precision variables so you can balance them out. Yeah,
A widely used type used.
widely used. You making fun of me? Well, that's where I had to stop because of Eric. So
Sorry, I'm
widely
behind trying to.
type of circuit
I didn't even notice that.
used
I didn't write it.
for measuring resistance.
Widely used type of circuit used for measuring-
So there's no
Yeah,
R4.
I didn't put
It's RX.
widely.
Oh.
Now I will warn you. If you get too critical of my writing,
So I was literally just
Start
trying
giving me
to
bad
say it.
time.
I was probably-
I have been known to stop writing and just talk. Let you figure it out. You probably followed the way I wrote it, so when I get tired, that's the first thing that goes is my spelling.
It's okay, I can't
The second
do
thing is
that.
my attitude. Get hangry. Okay, so 1, 2, and 3 are precision variable resistors. Rx is the resistor to be measured, is the resistor to be measured. Is the resistor to be measured. So we have a meter, and in this particular example, they put the galvanometer is inserted in the circuit to indicate the condition of balance. If the bridge is properly balanced, in other words, all four of these are 1, 2, 3, and 4, or X, I should say, are balanced, there is no difference of potential, and the meter reads 0. I don't say what P is. I think P is that's your actual an adjustment. So, in other words, if we could look at this kind of in a different light, you're asked to measure a resistor, and there you are right there. That's the one you're measuring. So we could say this is your like black lead from your meter, and this is your red, and this is your black one right there, and you put it across there. And if you just put your leads together and zero it out, then how much current flow do you actually have through the circuit? You'd have none because you've actually balanced it, and that's the whole point. And so when you put it together, you can see 0 on your meter, right? That's what you're doing. And then you take it out and you put, let's say, a 1 ohm here or something like that. Well, now you're out of balance. And so what happens is because you're out of balance, you have current flowing through here, and one side has less resistance than the other. You have a difference of potential, and that's going to cause current to flow through the meter, which is then going to indicate voltage, which will move your needle, which you see as ohms. So it's okay if you don't quite understand this fully, but it's the thing that you do. The takeaway on this is there is such thing called a Wheatstone bridge. It's used in a lot of things, and in this particular case, because they don't all work the same, well, they have the same principle. This one is hooked into a ohm meter, and you have the 3 resistors plus the 4th. Now, if this RX is exactly the same, and it's perfectly balanced, which you, in some instances of using a Wheatstone bridge, that's the point, you get it in balance, then you have no current flow through here because there is a total balance. Instead, it would run on the outside and around, and then you would have no flow through the middle. Your meter would say 0. If you have an imbalance in any one of these, you're going to get a flow, and then I wonder if it'd make more sense if you didn't draw it as a triangle for you guys. That's all right. I don't want to belabor that point, but then that's what you get as a flow. So I'll just finish this off, and let me see. A, B, C, D, A, G is inserted into the circuit, to indicate the condition of balance. if the bridge is properly balanced, the meter will show oops, I just jumped a line, hang on. The bridge, there is no difference. We'll just get rid of that. There is, because I'm reading it saying, nope, that was wrong. There is no difference of potential. And the meter reads 0. If the meter is out of balance, the meter will show an indication proportional to the out of balance.
Do you mean if the bridge is out of balance? Or is it-
Yes. So once the bridge is out of balance, then you're going to get current flow through the middle of it, which is then going to register on that meter, which is then going to show you an indication. The more out of balance it is, the higher the indication.
So why would you use one of these? Or when would
Well, for the ohm meter,
to
but-
make sure that the ohm meter is correct? Like,
no, it is the ohm meter.
Oh. Yeah, because there's resonant voltage on that.
Yeah,
Okay, oh.
that is an ohm meter. They just got to show you why I threw it in here. I don't remember. It's kind of a weird place to have put it. I think it was because somebody said, "Hey, you're covered in Wheatstone Bridge, right?" And I kind of thought, "Oh shoot, yeah, I'm not." So I put it in there. And I'm trying to think of other applications where you see it. You see it in a lot of different instruments. I don't think you really see it necessarily on schematics of aircraft as something that's just sort of built in. It wouldn't make sense, but definitely see it in meters and things like that. And a lot of times you're looking at schematics internal of things and you're going to say, "Wow, there's a Wheatstone Bridge right there in the middle." You know, it's like, so like I said, it's not uncommon to see them at all. So like I said, the takeaway is you just have to realize what's happening on there when they're out of balance and it flows through the center, and that's what you're going to get something on that. So, okay, everybody caught up? Eric, you doing good?
I'm good.
Okay. Talk about sensitivity. Some of you people are a little bit overly sensitive. Wait a minute. Never mind. It has something to do with something else. I was looking at my notes. I really thought this was going to be a good subject, but all right. Defined. Okay, we're talking about meters again. Defined as the amount of current flow needed to create a full scale deflection, So in other words, we have our Simpson meter, and we go to the 10-volt range. How many volts does it take to make it go full scale deflection? All right. I hesitated because we're really talking more about amp flow, because it's kind of, yes, that's true, but not necessarily. You're going to see how it is. We're on the 100 milliamp scale. How many milliamps does it take to go full scale deflection? Okay, that's its sensitivity. So in one respect, but here, so the Simpson has a DC voltage sensitivity of 20,000 ohms per volt. So what does that mean? Well, 20,000 ohms at 1 volt equals 0.12345 amps, which is the same as 50, 1, 2, 3, 4, 5, 6, yep, 50 micro amps. Not something, yeah, microamps. Microamp. By the way, you guys are ahead of the power curve because you know they've been talking about the coronavirus, and which is the big variant you're talking about now?
Delta.
Delta. What's the new one?
Sigma.
Sigma?
Mu.
Mu.
Mu. Yeah, they're talking about the mu, which is that little letter there.
Llama was the third or
I don't know. I've been hearing about the mu one on there. Okay. Well, how did I come up with that? Where did I get this? 20,000 ohms at 1 volt equals 50 microamps.
The Ohms Law?
So there's this thing called Ohm's Law. Maybe you've heard of it.
Like yesterday.
EIR. So if E is
1 volt.
1 volt divided by
20,000 ohms.
20,000, I hope that's what it equals. All right, so let me see. On the 2.5 volt setting, 2.5 volt setting, how many ohms would that be?
50,000.
5 times 0.00.
So 2.5 times 20K equals 50K ohms. Try it. Because remember, it's 20,000 per volt. So it's 20,000 ohms per volt. So it's times 2.5, so that'll be 50,000. So yeah, you'd have to. It's going to get rough. This little one. We're going to do a lot of Ohm's Law stuff. So that's what we're talking about. Yeah,
500,000.
that's what I wrote. 500K.
I thought it was 50.
50? Let me see.
For you, 500.
Well, I'm just going by what you're yelling at me. 2.5 times 20 equals 50,000. Okay. 50.0. All right. 10 volt setting. What is that? 10 volt setting. This would be 10 volts times 20K equals 200K. We sure? I want to get yelled at.
Just add a 0 to the 20.
I think I have a misprint here. Note that this is not the actual voltage of the circuit. All right, so understand that, and that's going to help you a little bit when you get into the battery project. This is going to be, don't go off my notes, go into the Simpson manual, look that up. It's going to tell you how many ohms, or tell you ohms per volt, and then using Ohm's Law, you can figure out what the current flow is going to be through there, which is kind of what we did. What is the current flow going to be at full scale deflection on this one, 2.5? How many amps are going to run through there? Full scale deflection. I know, Ohm's Law, come on. You guys falling asleep on me?
It's gonna be 5 microamps.
You don't sleep.
What do you get? Oops.
That same number, 0.0000, like 4 zeros and a 5.
Huh. Sure about that?
Five, six,
Yeah,
zeros,
you said
5
5
zeros.
5 micro.
1, 2, 3, 4, 5. 1, 2, 3. Oops, I got one too many. So 4 zeros and a 5?
Yep.
Interesting. How many is it going to be right here?
Same thing.
Same thing?
Yeah.
Because the ohms and the voltage is proportional.
Well, wait a minute. So does this mean I made a mistake?
Yeah.
No.
No.
Well, why?
Proportions. Yeah, they're proportionate to each other. Voltage and current are directly proportional.
Well, let's stop and think about what we're talking about. What's inside the meter?
Ohm's Law.
What's inside the meter?
What's inside the meter?
Magnets.
Magnets. And does the needle, needle is attached to a coil. Do I change out the coil?
No.
No. So if I put it on the 2.5 setting and I get a full scale deflection, it takes 50 microamps to make it full scale deflection, right?
Uh-huh.
Because I didn't change the coil that's wrapped around the little needle, did I? And I didn't change the coil that's wrapped around the stationary ones, did I? It's the same thing. So then I switch my lever on my Simpson meter and I go to the 2.5 volt setting. How many amps does it take to go full scale deflection now?
Same amount.
The same. Well, then I change it to 10 volt setting. How many amps does it take to go all the way to the end?
Same amount.
Why does it take the same? Same coils. Nothing's changed. So what you have to do inside of the meter is it has to figure out, or somebody else figured it out for it. And when you're switching that, what you're doing is you're saying, okay, we're going to have basically a resistor that's going to take all of this extra power. We got to get rid of it over here, and we have to just get this 50 microamps to run this way to show full scale deflection. So if I get on this setting 50 microamps, it's going to go full scale deflection. The rest of it's going through this resistor over here, right? So it's just setting up something with Ohm's Law. It's not real hard. So let me see, 8, 9. That makes no sense why I would say that. No, this is not the actual voltage of the circuit measured, but by the full scale deflection. I think I just kind of covered that. Meters have different ohm volts on each scale. Not all meters are the same, and the Simpson is 20,000 ohms per volt on all DC settings. Got that. All right, let me see. And why do you do that? Why have such a I should say it's important to have, and I'm going to change my notes a little bit, to have this very low current. So we're talking about volts, right? So I'll make this 0.4. How about that? So using a very low amount of current leaves the circuit, or the original circuit, how's that? The circuit you're working with, relatively unchanged. I was going to say, yeah, and I think I get into that, but I don't know if I want to really, I don't want to hurt you. I want you to hate me. I have this big point here, and I'll tell you what it is. So I do consider the following series circuit, and I draw this circuit on the board. Oh, what the heck. See if we can do it. 10 minutes. No, I'm not going to. I'm just going to tell you this. If I had more time, I would draw a circuit on the board, and it's just a very basic little circuit. The 100 volt battery. Why 100 volts? I don't know. Oh yeah, to keep it simple, a 100,000 ohm resistor and another 100,000 ohm resistor, basically in series. And then I'm going to show you the voltage drop on each one. And then what I'm going to do is I'm going to show you what happens if you use a meter that has a lot of resistance built into it, a cheap meter, versus one that is a high quality meter. And it changes the entire circuit when you start measuring stuff, because what happens is it sucks so much amperage out of the circuit to run the meter that it changes the circuit. And then it lies to you about the reading because it just sucked all the voltage or a bunch of current out of the circuit to make the meter run. So imagine, if you will, you've got like a very nice Simpson meter that has 20,000 ohms per volt. So it's got this huge resistance built in, which means that very little current is going to flow through it to make the meter work. That's a good thing. Now imagine, if you will, if I attached to your meter a 100-watt light bulb that has, I'm going to build this cool meter because, I can't see real well, so I can't see fine. But for people who can't, and so it's got a 100-watt light bulb that shines on over it. So, and it runs off your circuit. So every time you try and measure something with your little 6-volt battery and you go across there, this bulb starts kind of glowing a little orange, sort of working so you can see. What is that going to do to your circuit? It's gonna, and so it's going to completely lie to you about what's happening to the one thing you're trying to measure. Well, look at that voltage drop. It's 5.9 volts, It's like, well, it is now because you just sucked the life out of the battery. So that probably was a better example than everything I was going to do. So, but at least you could read it. So what we'll do is we'll figure out how to do it with a LED that uses very little. So, let's see.
Or you could just not read analyze in the dark.
Or I could just piss you off with all of this and make this point here, which I'll make a star over here just so you, because I went through so much stuff. Electronic VOMs, volt ohm meters or multimeters, do not have ohm per volt issues, which I was kind of surprised when I really got into that. I was trying to find out, because none of the electronic ones have this, what are ohm per volt. And so then I read about it and realized that, wow, it's just done kind of electronically and it doesn't have this problem. And so that's why you use an electronic one.
When you say electronic, do you...
Digital.
Okay.
And let's see, I will rephrase this or state it again. So voltmeters have very what resistance? High or low? Okay, and you want a very high resistance. And remember, you can do this because if you have a battery and I connect a voltmeter up to it, what happens to the voltmeter?
It still works.
It still works because it has very high resistance, and so it's only going to allow how many amps to go through it? If I do that right there? About 50 microamps are going to go through there. That's not too bad, is it? Okay, so amp meters have very what resistance? Low. That is because if I want to connect an ammeter up to see what my current flow is of that battery, how many amps do I get? All of them. All amps. That's wait, we could, how about this? Can I do it? Let's see. Drop funny. Infinity amps. That's how many amps. You get all the amps that go through the battery. But only for a very, very brief period of time, because
Magic smoke comes out.
pop goes the circuit breaker or the fuse. All right, so you can't do that. That's why, because it's very, very low. It's a short circuit. And so it does not like it at all. All right, so moving on here to, that was all about voltmeters. I know, you still have. So let's talk about amp meters. Or I'll spell it the way I spelled it here. A-M-M-E-T-E-R, ammeter. All right, and an ammeter, of course, measures current flow. Current flow. You know that. And boy, I can abbreviate a whole lot of stuff right here. And ammeter works on the exact same principle. By the way, somebody once corrected me that it's not principal with the P-A-L. It actually is. I changed all my notes. I'm like, oh yeah, I guess you're right. And then I was like, no, as a voltmeter. As a volt. So there, just repeated all that. The exception is that an ammeter is connected in what? Series. So that all current flows to the meter. And of course, if you had a very, very high resistance ammeter, what would the current do? Kind of stop. It wouldn't, it'd flow, but not too much. All right, well, they're leaving. One more point. For very small amounts of current, the internal coils can handle the load. And for, it won't make sense if we start here, for currents over, I'll put this, say about 10 milliamps, a shunt is used. And a shunt, like shunt the front door? No. Shunt simply means parallel. So shunt means parallel. So if I say shunt wound motor, it means parallel. If you have a shunt in something, it's a parallel thing.
Not like metal.
Even in medical, I was going to think medical, you can have a shunt installed. It's a thing that is parallel to your vein. Stint is, no, they actually have shunts and stints. I don't know what the difference is. Shunt simply means parallel.
That was a good learning day.
That was a lot.
Ohms Law.
Ohms Law.
That's what's inside.
You know what? We might be on track. I think we'll be okay. We'll see how it goes.
I can tell you now.
You know what we could do? I could put it